Unit 14, Part 4. So we're doing a sample proof. We've just transformed these by CQN in order to get formulas in quantifier form. Right? We recognize this is not O, transformed it to A. Recognize this as not E, transformed it to I. Now look at the conclusion, right? I have to think about my conclusion. Just at the bottom line. That's my conclusion. It is. We also have to say of it, right? This is also the thoughts you have to have when doing the proofs. You have to recognize that it is not in quantifier form, right? It is a negation. Begins with a negation. Doesn't satisfy the first condition of being in quantifier form. Doesn't start with a quantifier. It starts with a negation. That's very important because you have to think to yourself, I'm not going to be a. I'm not going to. You have to think. I'm not going to be able to. Right. So what? It's always the same. It's the same thought when you're doing proofs as always, right? What is the form of that thing? It is a negation. What rules allow me to derive negations? There's not many indirect proof. Indirect proof. You could actually. This would be perfectly fine to set up for an indirect proof here. You would assume for all x, you would assume that universal statement would actually be a good strategy here, but let's not get into that now. But the other thought you should have, another possibility of how to go about doing this proof is, and the thought you must grasp is, I certainly cannot get this by the generalization rule, right? By the one of the four rules governing the addition and subtraction of quantifiers from Unit 15. I cannot use those rules to infer this because this is not in quantifier form, right? This is not in the right form to use that rule. But I do know that I have the CQN rules and I can transform that, right, working backwards. Right, I could, or rather, more explicitly, your thought is this: I can derive something which is in quantifier form that is equivalent to this by CQN, such that when I get that equivalent formula by what? By a generalization rule, which I will be able to get that formula by a generalization rule because it is in quantifier form, then when I have that, I will be able to infer this by CQN. So CQN is going to be the justification for the last one, but you are thinking the CQN backwards here, okay? And how do we do it? Well, again, you grasp this is what? This is a, without the negation, it's for all x, if f, then not h. That is universal exclusion E form, right? So that's a not E, right? So I've just got square brackets over here. This is just in your head. You don't put this on the board. Not E, thinking CQN backwards. A's go with O, E go with I, so not E goes to I. And this is I form, right? I've just laid down the I form. And just doing symbolic manipulations, I can just plug in the subject and predicate, being clear, please, that the predicate is H, the predicate is HX. It is not the case that the predicate is not HX. That's part of the form. We looked at the negation sign and we grasped that as part of the form when we said this was E form, right? If we didn't grasp that as part of the form, we'd say it's the negation of A form, that the whole thing is A form with a negation sign at the top, right? Because for all x, fx, hook hx, that's an A form, that's universal inclusion. Negation is part of the form of the E form. Okay, so it's just the hx, which is the predicate, when I'm doing these. So that's the symbolic manipulation from not E to I, just thinking the symbolic rule of the CQN. Say it out loud to make sure they're equivalent. Not all f's are not h. So some f's are h. Yes, those are equivalent. If not all f's are not h, and some f's are h. Yes. Okay, so now here's your basic strategy in proofs when you've done that. Right. The reason why we're doing this in lecture on Unit 14 is because this is the use of the big lesson of Unit 14. Right, doing these transformations. Oh, look. My kids are doing proofs. Isn't that cute? Yay. Very good. They're not by themselves. That's pretty excellent. Notice how they've indented from the main line to for the subproofs. Very good. All right. That marks kids. Okay. When you've got it now in this form, okay, here's the thought you have. So look what we did. The premises, we had these two negations. We transformed them into equivalent formulas, right? These are things in quantifier form which contain all the information on 1 and 2. Basically, you forget about 1 and 2. You're not using those premises for anything. All the information that's there is in here, and what we're going to do with these is instantiate from them. Use the instantiation rules. For this one, universal instantiation. For this one, existential instantiation, right? And we're going to do truth functional reasoning, that is, the modus ponens and the modus tollens and the simplifications, and so on, right? On the results of the instantiations, because the results of instantiations are going to be conjunctions and conditionals, or a conjunction and a. This will be a conjunction and this will be a condition, as we see. So you'll see an instantiation. We'll talk more about it in Unit 15. And then we're going to get a certain conjunction. It's going to be FA and HA, but from we're going to get a certain truth functional formula, FA and HA, which we will be able to recognize once you've learned the rules for Unit 15. Recognize as something which counts as or is in the form of a premise for an existential generalization, right? The bit we've done already, going from the not E to the I form, was getting getting a formula equivalent to this, but which is in quantifier form. That is in the form of a conclusion of existential generalization. Right? It's in the form we need to be able to use the rule. Right? Yeah, just as an indirect proof, for example. To use indirect proof, your conclusion has to be a negation. Right? The conclusion of indirect proof has to be negation, right? Or say you've got a disjunction and you want to use conditional proof or you need to get a disjunction. You've got a disjunction as a conclusion. You want to somehow use conditional proof to get it. You have to transform that disjunction into a conditional, which you can do by double negation and double negate the left disjunct if you have to, and then transform it by conditional exchange. Then you have the thing in the form of a conditional. Now it's in the form of the conclusion of the rule of conditional proof, and you can use conditional proof, right? Similar thing going on here, right? We've transformed it into the EX, the positive I form, right? It's in quantified form. It's in the form of the conclusion of the generalizational. Okay, so now I'm just going to show you how you do instantiations and truth functional reasoning. A lot of your proofs, especially what I'm going to be calling the pure quantified proofs, much practice with which you'll get in exercise 2